Okay, good afternoon, everybody. So we are in the second class of the second week. Okay, so what did we do last week or last class? What did we cover? Yes, one second. Current. What else? Yes, what's that? Drift current, and what else? Diffusion current. Very good.
And also thermal voltage.
Okay, good. What's the thermal voltage? Who knows? Raise your hand. Thermal voltage. Excellent. So it's the ratio between the diffusion constant and the mobility. Excellent. Very good. So who is responsible about the diffusion current? Wait a second. Raise your hand. The majority carrier or the minority carrier? I need some hands there. Still, that place is gloomy. Go ahead.
Majority, because when the hole goes from the high concentration to low.
What about the electrons?
Also
Same thing, exactly. So the diffusion current is usually by the majority. We'll see also today. And what you call it? The drift current. Who caused the drift current?
Electric field.
Exactly. So whenever there is an electric field, there is a charge, that current is called a drift current. Very good. Nice. It seems that we are doing a good job here. It seems that the channel will stay for now. Unless you decide to sleep, then boom, the channel will go offline. Okay? All right, good. Thanks so much for that, because you will find what you studied so far very useful for today. So today, inshallah, we'll touch the first component, the first device of this course. The first device is called the PN junction. Okay? The PN what? PN junction. You know what we mean by the word junction? Anybody knows? What's the meaning? إيش المعنى? What's the meaning of junction? Word of junction. Yeah, what's that? No. That's not. That's fine. Mistake's fine. Okay. Junction. Who has another definition? Any definition. If it's crazy, show it to me. Just tell me. Junction. What means junction?
Fill something in the hole.
No. No. Yeah.
to connect two things.
Yeah, because we are talking about that here. Very smart. But you are close, but you are getting it from here. But the meaning of junction, word, yes.
It's like
A node. Close. There's a meaning of that in the node. Yes, there is a little bit. Yeah. Who knows? Was that? Raise your hand. I need to see who is talking. Who? Yeah. Junction. What's junction? What's? Throw anything. Even if it's a mistake, it's fine. Because I don't blame anybody about a mistake. Yes.
meeting point for.
Very good. Tamadar, got it. Right, Tamadar, huh?
Yeah.
So it's a meeting point. If you are driving with a car or something, you said there were two cars met at a junction. So when there is two roads, for example, when they meet at an intersection, or called also a junction. خلاص? So هي نقطة الالتقاء. Okay? That's what it means in Arabic. Okay? You understand? Good. So the junction is where two things get joined. That's why the knot, عقدة. Okay? Where two things meet. Do you understand?
Yes.
Very good. So what is two things are meeting here? We are meeting the P-type semiconductor with an N-type semiconductor where here. What's called here? خلاص. Now you know what's junction. Difficult? No, huh? Simple. صح?
Yes.
Excellent. All right, good. So now we are trying to learn what's this device. Very good. So the P-type side of this whole thing, of this junction. Now when we say junction, automatically for us in our brain, we imagine an N-type semiconductor meeting a P-type semiconductor at a certain point. Okay? The P-type side of this junction is called anode. Okay? And the N-type side of this junction is called cathode. We need to give names, right? For things that we learn. Alright, these two semiconductors, P-type, is connected to a certain terminal, terminal like electrode, something like that, with a certain contact. Is called ohmic contact or metal contact. We need this later to send electric current or to get electric current. Depends. Okay. So we have what we call metal contact between our semiconductor and our terminal, right? That's it. Very simple, really, seriously. That's it. These are not that important for you now, but it's just later on when we use this somewhere else, we'll see how useful is that. But for now, this is what we need to have in our mind. The anode, the cathode, and there's a junction between them. That's it. Halas? We're not doing, yeah.
We said that we have those nodes because it will, we can connect the current, right?
We can, we need to use this junction somewhere, so we need to connect it to a circuit.
So they
It's like a resistor, for example. Yes, go ahead.
So they have signs that we can know the direction.
Yeah. We'll get to that. Don't worry. We will start by the simple picture here, and then we will talk about the sign, the direction, etc., etc. Don't worry. For now, we are just taking it easy to understand what it is, and then little by little we build this. Any question there? No question. Good. All right. Very good. So let's move on. What is the state now of the PN junction in open circuit? Open circuit means what? Means that this junction is not connected to anything. It's open. في الهواء. خلاص? That's what it means, open circuit. You understand? Good. Now the question is, what's the state here? What's the state? I know United States. So what's state here? What's? State here means what is the condition? How does it look like? What's going on inside this? Okay, good. So to know that, we go back to our understanding of semiconductor. We know that N-type semiconductor has the majority carrier are N-type. Electrons. Alhamdulillah. And the P-type semiconductor, majority carrier are holes. Is the semiconductor charged or not charged or neutral or what? The semiconductor, N-type or P-type, is it like charged positively or negatively? Like for N-type semiconductor? It's neutral. It's not charged. You see, although the majority carrier for N-type semiconductor are electrons, but still it's neutral. And the same thing for P-type semiconductor. Some student last time, they thought that it's like charged electrons or charged holes. No. We said majority carriers means they are ready to move. Right? But they are not. It's not ionized. It's not, it's not ionized. Sah. Good. So what happens there for N-type semiconductor, for example? We have majority carriers are electrons. Who gives them? Who made them? Who gives us this? Electrons. Who?
Electric field. Atoms.
Which atoms? Not silicon.
Phosphorus.
What we call it? It could be phosphorus, it could be something else. What we call them? No. Donors. I see. Now it becomes Please revise. So N-type semiconductor has majority carrier electrons, and these electrons comes from what? From the donors. They give them. Donate. Good. Sah. Now the donors, when they give electrons, they become what? They become positive charge. Hey, very good. Sah. They give electrons free, and the electron is free to move around. But they are what? They are positively charged. Yes or no?
Yes.
We call them bound positive charge. Bound positive charge. Why? Because they are bound in the crystal, means they have already created what? The covalent bonds, right? Remember? With other silicon atoms. Yes or no? So they are bound. معلقين, مربطين. خلاص. That's it. They are stuck. You understand? And they are what? They are positively charged because they donate already an electron. Clear? Excellent. Now they donate electrons and they are bound and blah blah. So now the electron, where is it? They are positive and the electron is negative, so the electrons go around them basically to keep them basically neutral. Because when we add the positive and negative, it becomes zero. We are fine. So the electron will turn around this donor to keep it neutralized. Okay? So things are neutral still. Okay? But that electron has a very weak force with this atom, with this donor, so can leave any time. If there's this electric field, boom, bye-bye. See you. Okay? خلاص? So the same thing for the p-type material. So in that case, we will have what? We have the negative bound charges, yes or no?
Yes.
Which are what?
Acceptors.
Acceptors, excellent. And the hole will turn around them. So whenever you have some story in the n-type, in the p-type, it's just a mirror. Okay? Just flip everything, you are in the other side. فهمنا ولا لا? Very good, excellent. I just remind you, if I see anybody with the mobile, I'll ask her to stop. We agree that mobile is not allowed. Okay? Please, do not tell me to do that, please. Alright, some of you do this kind of mistakes, but I need to remind. Fine, good. So this is the story. We are not still answering the question, what's the state? What's going on? Khalas, we understand this. We are not going to discuss this. So what happens now? That's exactly the best question. What happens when a PN junction is newly formed? For example, we just touch them. Boom, what happens at that time? Sah. What happened? We see next. But before we see next, let me ask you. So let's use the blue. So this is the junction. This is the p-type. This is the n-type. Okay. What are the majority carriers here?
Holes.
Excellent. So which color you like? Green? Let's use green. Right? Holes. Too much of them, huh? So holes are, boom, the top. Now minority carrier here, who are? Let's use different color. For example, and they are like, minority, أقلية مستضعفة. صح ولا لا? You understand? مساكين. Very poor people. Now, on this side, who are the majority carrier of the n-type semiconductor? Excellent. So let's do some music here. My goodness. I remember my mom when she was cooking, she used to, there's what you call kisra, and she put holes there to make it, breathe or something. So she likes, and I was watching, like again. So I like that music. So the electrons there, they are the top, they are the highest, majority. Huh? Now the holes where they are?
Minority.
Very good. So let's get to the holes. The holes I like. And here it just is it's a way of showing, but it's not exactly like that. So very these are the minority. So let's see. So let's look only at the holes. Huh? So holes, their density is like this. Is high, 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 and then goes low, low, low. Why this is low? Because we said that the thermal generated carriers are way, way less than those created by the doping. Remember that? صح ولا لا?
Yes.
So that's why we say this is high, this is low. صح. And let's go to the electrons. The electrons, they will go what? They are like small, 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 and then boom, they go high. Yes or no?
Yes.
Excellent. Now somebody tell me what's going on when we just meet them.
Diffusion.
Very good. Why?
Because
Oh wait, خليها. Give her a chance.
It's
Yes.
from high.
Explain. Yeah, go ahead. Try. Yeah, what will happen? Diffusion, صح? Diffusion between what and what? Diffusion of what? First of all, what is diffused?
The electrons and
Electrons, صح. The electrons they move from where to where?
from the hole to the other side.
صح. Is there?
high concentration.
Yes, صح. Just a second. From where to where? Here is the picture. You tell me.
Electron go from the high N type to the P type.
Exactly. So the electrons, they will move this way. We'll use the red because we represent the electrons by half. So I will holes. Holes. Yeah. Last one. Yeah. Go ahead. The opposite direction. So the holes, they will go what? They will go the opposite direction. Why? Because they are high in the p-type and low in the n-type. Alhamdulillah. That's it. You answer the question. So next time you can teach this course. Very good. So this is what's happening. Okay, let's move on. So this we already know. So basically what does it say here is that the free charge was, this is the negative bound charge. What they are exactly here in the p-type? What they are here? The negative bound charge in the p-type. This is the p-type. Remember this? This is the p-type. So negative bound charge, they are what? They are, we just talk about
Acceptor.
yeah, that's what I'm saying. Acceptors, they create the holes. صح ولا لا? So these are the acceptors. Yes or no? And around them move the hole. Yeah? Yes or no? Same thing for this, but instead of acceptor, we have what? We have donors. Those nice donors here. Nice, fancy. With a positive charge. And around them move what? The free electrons. Yes or no? Excellent. So this is the n-type. صح. Excellent. Thank you very much. It's just we are trying to. So the electrons here, they went to the p-type. Yes or no? And the holes, they went to the n-type. صح ولا لا? Make sense? We are good. But then they disappeared. Why? Why they disappeared here in the diagram?
What's positive cancel negative?
What's called?
No,
What's called this?
Neutralization.
But there's a more precise word. What's that? Who knows what's called that? Why they disappeared?
Attraction.
Yeah, the attraction. Okay, then why they disappear? Attraction, they start to come together. صح.
It's cancel
They,
each
yeah?
other. Cancel each other.
Yeah, what's called that cancellation? Yeah.
They can.
What we called it. Yani we studied it, or you forgot about it, or we didn't find it, and you are using other words just to cover up that one. Nice try. What's the exact word?
Equilibrium.
Equilibrium هذا التوازن لما when everything settled down. No. The phenomena, yeah? No, the junction is where they meet, but why they disappeared? The electrons went that way, the holes went that way, thank you very much. But when they meet at the junction, they disappear. Did you see that? What's that? Who's that? Who answered that? Yeah, you. Very good. Did you read it?
What?
Did you read it from the... Very good. That's exactly the right word. They recombine. Because we said the generation is to create them. Now, when they disappear, we call it recombination. Write it down. Write it down because that's important. Huh? So they recombine. When they recombine, bye-bye, they are gone. Okay? They are gone. Okay? Because whenever there's a hole meeting an electron, bye-bye, there's end of story. They disappear. Khalas, that's it. But then, the electrons here on the n-type, they left behind them what? They left behind them a donor. Yes or no?
Yes.
The donor that is what? Positively charged. See here? Now they are not neutralized anymore, this bound charge. صح ولا لا?
Yes.
Make sense? The same thing for the holes here. When the holes moved, they left behind them what? The acceptors, correct? And they are what? Negatively charged. And they are not neutralized. They are not neutralized means there's an electric field. Now they can show people that yes, I am charged. صح ولا لا? Positive charge or negative charge, correct? Good. That's what happens. All right, what's next? Seriously, the bound charge, they do not move like that. They are stuck. So really that motion is not of a big deal. It's not really real. What's real is that these bound charge here and here, they are uncovered. And absolutely when they have that, what they do, they create between them what? Electric field. Very good. Now, this picture where you have negative charge on one side and positive charge on the other side, what does it remind you? You have seen this before, yes or no? What does it remind you? You have seen this before, yes? You have a negative charge side and a positive charge on the other side. Very good. That's exactly what's happening here. So, there is a creation of certain capacitor here between the n-type and p-type, right at the junction. Okay, this is the positive plate and this is the negative plate. And between them there will be what? Electric field and or, if you want, a voltage. صح ولا لا? Make sense? There's a voltage between the capacitor plates, correct?
Yes.
You can measure it. صح ولا لا? Very good, excellent. Now what happens if there is any, like for example, let's see here. If there is a hole here, say there is a hole here, a nice hole here. Where is that hole? And we are in the N-type. What does it happen to that hole? Go to the right or to the left? Hi, معلش. Hole is in here. First of all, before we answer this question, wait. Let me say, whoa, just a second. Okay, now where is the electric field? Which direction here?
With the same direction of the electrons.
Positive to negative.
Positive to negative. From the positive charge to the negative charge.
From N-type. From
Hey,
N-type.
yeah, I know, I understand. But the exact answer is from the positive charge to the negative charge. Hadi. Do you understand? We know that, huh? So this is number one. We know the electric field. صح ولا لا? It goes from the positive charge to negative charge. Now, the question again, if there is a hole here,
In the same direction.
Same direction.
so it goes where?
From inside
From
to
inside.
Very
to
good.
negative.
The holes here in the N-type, they are majority or minority?
inside minority.
Exactly. So the electric field that is created here at the beginning, it will try to push the minority carrier in this side to this side. Yes or no? What happens if there's an electron here in this side?
Opposite direction of electric
Very good. So this electric field will push the electrons, which are minority here, where? To the N-type. Yes or no?
Yes.
Okay, very good. So this electric field will try to clean that area from any charge actually. Yes or no? If there is any hole or electron here, it will push them. And there are minority holes in the N-type and the electrons on the other side. And that's it. So there's two things. So there is first the electron, the current, that is the diffusion. The diffusion will create this zone. This zone, we call it what? We call it depletion region. And we call it depletion region because it's depleted of free carriers. Depleted معناته مفرغ. فارغ. Zero. نقوله مثلا, we say the battery is depleted. معناته it has no charge. No, ولا لا? My mobile battery is depleted. Bye bye. I have no charge. I have no power. You understand? Good. So that's what it means, depletion. So, or we call it also free space area. Free space يعني free of any free carriers. Okay, it's empty. فهمنا? Good. That's it. So that's gone. Bye bye. So basically we had initially the diffusion current, and then the diffusion current creates, because of the combination, creates the depletion region, and the depletion region will create a, what current is this one? The electric field is pushing the minority carriers from this side. The drift current. Very good. So diffusion current create depletion area thanks to the recombination, and then from the depletion, we create a drift current. See, story nice. See, it's not bad story. Very good. Thank you very much. We move on. I'm not going to answer this because it's obvious. Now we get to the voltage. Very good, very good. This is a nice picture here. So we have here positive charge and here negative charge. The voltage of positive charge is always bigger than the negative charge. Always. Huh? Very good. And when there is a voltage, there is electric field, of course. صح ولا لا?
Yes.
What's the relationship between electric field and voltage?
E equals Q times
No, without Q. We're not talking about Q.
VD.
V. VD.
Forget about the exact equation, the exact differential equation. D what? The electric field is equal
So minus V
minus معلش
minus
minus
V.
gradient. Very good. اللي هو if we are in one dimension dv over dx. صح ولا لا? Make sense? So the gradient is basically the slope. صح ولا لا? The slope, and is opposite of that slope. In any case, So this times the vector I. Very good. So now, this voltage that we have at the junction is actually only at the junction. It does not show between the terminals of this junction. Means that this side to this side, the voltage between this side and this side, so let's take a different color here. Let's say green. So the voltage difference between this side and this side, delta V, is equal to what? Is equal to 0. That's why this actually is called also another name, diode, but for now we are just calling it junction. The diode is nothing but a junction, okay? So if you have a junction, you cannot make a battery because that voltage does not exist here at the terminals, okay? It exists only here.
In the junction.
Only at the junction. Outside the junction, boom, is 0. Do you understand? So the voltage here is the same as there. We cannot feel it. Do you understand? Good. So, why we can say that? Let's see why we can say that. If you solve Poisson equation, who took electromagnetic course? Poisson equation. Why we use Poisson equation? It's Maxwell equation, صح ولا لا? Which number? Which number? Poisson equation? Number 1, 2, 3, 4. That is 4, صح ولا لا? So which of electromagnetic course? This is Maxwell equations, yes or no?
Yes, but
Yeah, Mr. Maxwell equation.
but it's for Faraday's law, right?
No, Faraday, that's a different story. He has 4 equations.
Yes,
صح.
2 for Gauss.
Now we are talking only about the equation that we call it Poisson equation. Poisson equation is one of Maxwell's equations that allows us, it's actually from Gauss as well. Sometimes Poisson, sometimes Gauss, is used to basically allow us to enable us to measure or calculate the potential from the charge. Give me the charge, I give you the potential. And now, you understand? So it's something like this, very simple way. And if you solve that Poisson equation for a plate, for capacitor, so there is a, let's see here, which color is the best here? Oh, let's see the green? No. Let's see the blue. So blue is even worse. Let's see, the green is arham. Okay. So here we have the 2 plates in the middle. Here we have a plate and here we have a plate. Here actually positive charge plate, and this is negative charge plate. If you take that and you solve it in using math, here in this case MATLAB, you can see that in green, that you can see here, 0, and this is the potential. Potential means the voltage, yes or no? You can see it's green everywhere. Green, 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 green. Even in the middle is green here, green, green, green. That means it's 0 everywhere there. You understand what it means? That it means it's 0 here, and it's cross here 0 in the between, in the middle, and at the end is 0. Do you understand now? Good. So that's what it means. So the voltage is 0 everywhere outside the plate, in the middle of the plate as well. And in between is very high for the positive charge and very low, negative, basically, in the negative charge. And this is the electric field. And this is the most easy one to see. So this is just a proof of that. If you go to this link, you can see maybe MATLAB. Who is familiar with MATLAB? Who knows MATLAB? You don't know?
We know MATLAB, but we are not familiar.
Yeah, you better be familiar because it's a nice tool, okay? Try to learn it, It's a nice tool for you to do things that are really interesting, okay? All right, good. So let's move on. So the voltage only will happen, only the difference of voltage will be only in between the junction. We call that voltage the barrier voltage. Why we call it barrier voltage? Let's see. If there's a hole here, in the p-type, that hole comes, it's like it sees that there's a huge diffusion. I want to diffuse there because I have minority there. Following me? Now when it's trying to move, it's moving, and it's now it's here. Now it's going to jump here. And then it finds the electric field. Where's the electric field here? It's going from where to where? It's going this way.
Yes.
Very good. So the electric field will apply electric force on them. Yes or no?
Yes.
Which direction?
The electric field.
The same direction of electric
So that means it pushed them what?
to the
Push them back.
Beta.
Push them back, you see? I'm here, electric field, I'm pushing now back those holes. They see that there is a diffusion. I want to diffuse, there is a gradient. صح ولا لا?
yes.
So push them back. Stay where you are. And here, if the electrons here, majority comes here, what happens? It will also apply the electric field and also will be, it will be against now the electric field. صح ولا لا? Push them back. So the role of this electric field here in the junction has two roles. One is to push the majority carriers back where they are. Okay, tell them stop. Okay, that's number one. Number two, you try to push the minority carriers to their areas, like for example the holes in the N junction. Try to push them only in the depletion region. Try to push them, the holes, to the p-type and the electrons in the p-type. Push them to the n-type. That's it. These are the two roles of the barrier voltage. And when we say barrier voltage, we are talking about the electric field. خلاص? It's a little bit spicy, yeah? It's very important to understand this. Okay, good. Any question? Any question? Clear? Yeah, let's move on. We saw this, bingo, bingo. So this is what happens, boom, boom, and then depletion will grow. So at the beginning, the depletion region was small, yes or no?
Yes.
Few charges only are combined. And when the more, then more it will grow. صح ولا لا? More unbound charge becomes exposed. Will not become what? Neutralized, if you will. Their charge now, it has nothing to hide it. صح ولا لا? Nothing to cover it. Now we create the depletion region to grow bigger and bigger. And when that bigger and bigger, what happens? Now the electric field becomes stronger and stronger. And the electric force will push this guy to stop more and more until tell them that's it. You stay where you are. You are not moving. You have a passport that is strong, fine, okay, but we are closing the borders today. Stay where you are. You understand? We shut down the airport. It's like the airport. Do you understand? It's a junction from one country to another country. Class? Understand? Very good. Now what happens? We said that, and we said that as this depletion region increased further and further, if it finds any minority carrier here or here, it pushes them to their areas, and in that case, it will create a drift current. صح ولا لا؟ لأنه drift current is created by the electric field. Understand?
Yes.
Very good. So two versions of explaining what we call the equilibrium, التوازن. When things settles and everybody is in place, خلاص, and everybody is happy where they are. So what happens now? توازن. توازن means things will not change after that. They stay where they are. So what happens at that time? There is two ways of explaining this. There is one way that we can use. We say that the barrier here becomes big enough to push anybody back. Okay? To say, hey, listen, you guys, you holes, stay where you are, and you electrons, stay where you are. I'm strong enough to stop you. Or we can say, okay, fine, I let you go, boom, on the other side, but you listen, you know what? Any minority carrier, I push it back. So the hole comes here, okay, fine, there's gradient, I will send you a hole from this back. Okay? So as the holes comes, I will send as majority, I will send them as minority back. The same thing for the electrons here. As the electrons, they move the other side, this barrier will say, oh, why? Okay, you are coming, I'm sending you your people back. So, زيادة من هنا, نقصان من هنا, what happens? Exactly. At the equilibrium, the diffusion current will be equal to the drift current. So IS here represent the drift current, mark that, and the diffusion current is diffusion current, ID. Okay? You understand? That's it. At equilibrium, now what comes in goes out. So things are stabilized. مستقرة الأمور. وكل أمر مستقر. Now, at this time, the junction now is خلاص. We are good. We are fine. We have nobody comes in. I mean, what comes in comes out. So things are now settled. خلاص, finish. Now the good question is, how much is this barrier? Barrier in meaning means حاجز, سد. سد actually is a dam, but barrier تقدر تقوله حاجز. So it's trying to stop this diffusion. That's why we call it barrier. So what's the value of this barrier? Is this equation. The barrier voltage depends on the density of acceptors and the density of the donors, and also on the crystal itself, on the intrinsic density of the charge, which represent the broken bounds, okay? The thermally generated charge. So VT, what's VT by the way?
Thermal voltage.
Thermal voltage times logarithm Neperian, base E of NA, and D divided by NI square, okay? Don't worry, I'll give you this equation later on, because it's a bit bigger. For small ones, I don't. For big ones, sure. So this, don't worry, you don't have to, but just to imagine something here. So this barrier, let's see what it depends on. بما تتعلق, okay? What does influence the value of V naught? صح. VT has what? VT is equal to what, by the way?
The diffusion over the mobility.
صح, fine, it's okay. VT is diffusion over mobility. صح, but there is another equation. Because that one is like a ratio, that's it. So we need, what does it depend on parameters? More accurate equation. Which one? Equal to what? We call it thermal voltage. صح ولا لا? What is thermal? Show me the thermal thing. Why we call it thermal? صح?
Temperature.
Hey, how? Show me.
Sorry.
صح. My question now, the next question. Did you read the slides or not? Now, very good, excellent. So that means you are not listening. I told you, when you go home, you revise. صح ولا لا? So the thermal voltage is equal to what? You see, I told you to revise. I told you. So remember what we call. Why you call it thermal? Because there is a temperature. صح ولا لا? Makes sense. But how? If you revised, you would have known that formula. It's very easy. It's equal to K, or KB, Boltzmann constant. صح ولا لا? Times T, the temperature. Now we can see temperature. صح ولا لا? Thermal over Q. This is VT. We have talked about it last time. صح ولا لا? Make sense?
Yes.
We did, صح? That's the equation. You should remember it because it's an important equation. And it's thermal because of this parameter, temperature. And it's voltage because the units, when you calculate them, you find voltage. Understand? Now, if the temperature increase, the VT, what?
Increase.
Yes. So temperature increase, this increase. So, NA and ND, do they change?
No.
No, because we put them, خلاص, that's it. The number doesn't change. What? Atom will change from acceptor, from silicon to acceptor, يعني مثلا يعني. No. Do you understand? So the numbers, these numbers, they stay constant. But Ni change with something or not? Ni, the density, the intrinsic density of carriers.
No, because we don't have diffusion.
But hold on a second.
It will
We discussed about this, yes or no?
Yes.
It has equation, yes or no?
Yes.
What did we say about this one?
Increase with the temperature.
Exactly. There's equation we studied. Is actually equation number 1. Remember that? You are not revising. You did not watch my video.
What?
And the quiz is actually next week. But with this was the first equation. This is equation number 1. It was the first equation we have talked about it. This was equation number 1. We said that the intrinsic density of carriers increase with temperature. Yes or no? Remember?
Yes.
It was something B
B.
T power 3 over 2. صح ولا لا? Yes or no? And then E exponential band gap minus band gap divided by 2 KT. Yes or no?
Yes.
See, I remember.
But Dr. equation, we don't memorize.
I understand, but at least try to remember that with temperature this increases. I agree, the equation is too big. You are right, 100%. But at least I know when I increase the temperature,
The N
this increases. Ni, not N. Ni increases. Because the equation of Ni shows me that when temperature increase, Ni increase. Remember that, huh?
Yes.
Very good, excellent. So, V naught depends basically on only one parameter, and that is temperature. Because anything else, of course, it depends on the acceptors and donors density, but they are fixed. They don't change. The temperature can change. Understand? صح ولا لا? Yes or no?
Yes.
Yeah, that's it. So this is number one. The value of this, typically, in when we make these junctions, it's between 0.6 and 0.9 volt. Just to give you a range. Okay? مثلا لما تروح سوق السيارات والله what's the range of سوق السيارات والله شوف مليح between 60,000 و 100,000 درهم يلا تفضل وانتم ما you check your pocket صح ولا لا؟ Now the same thing here. The range of the voltage is between 0.6 and 0.9. It's not 2 volt, it's not 5 volt, do you understand? So this is the range, مجال. Okay, do you understand? Everything has a range. مثلا عمر الإنسان has a range. Between 0 يعني people can die at the birth, or let's say 100 مثلا 100 recently 145 years. Yes or no? Good. So everything has a range. The range of this voltage, barrier voltage, is between 0.6 and 0.9 volt. Excellent. This voltage will not be sensed at the terminals. We have said that because we cannot make batteries out of junction.
So
Very good.
doctor,
Yes.
barrier voltage will increase with the temperature?
This is a good question you need to answer. I leave it with you. This is a very good question. You need to think about it all. And the smartest one who can send me, without bribing or saying, an answer tonight would be considered for a bonus. والسؤال bonus from now. With temperature, V naught increase or decrease, يعني when we increase the temperature. If you want to write it from right to left. When we increase the temperature, is the barrier voltage increase or decrease?
Increase.
Well, I think about it and let me know how.
Because
No, there is no because. There is an email. Send me email. Let me think. خلاص? Good enough? خلاص? Keep the answer for you. And let's see what we can have. If you convince me about your answer, I will consider it as a good answer. Good? خلاص?
Yes.
That's good. We'll discuss the answer next week, inshallah. Remind me. Okay? Very good. So IS is which current? Drift current or diffusion current? We just talked about
Drift
drift current. صح. Is made of what? Majority carrier or minority carrier?
majority. Minority.
Really? IS? Let's go back. Hi, let's go back. احنا قلنا ايش الدريفت current? Okay, hold on a second. Drift current happens in the depletion region. Now, okay? And that current that is created from the depletion region is pushing actually the minority from this side to that side and the minority from his side to that side. So the drift current is always, in this case, in the junction, is made absolutely of minority carriers. أمنا ولا لا? Clear? Clear or not? So that's good to make a mistake. It's okay. This way you will know. If you don't mistake, you will not know. صح. Let's move on. So let's go there. So because the drift current is made of the minority carriers depend on what? They are created from where?
Dip.
Electric.
No, just slow down. Huh?
From the injection.
Yeah, but who created them? Where they come from? For example, me, I come from dad and mom. They have their names. You don't need to know them. But that's my origin, okay? Now these guys, also, the minority carriers, they come from somewhere.
When they are combined.
Depletion.
No.
Depletion.
No. From the broken bones. We said that they are thermally generated. Remember that?
Yes.
Again, by revision, you should know that. You understand? Minority carriers, all they are made from the broken bones. Remember that? We talked about that. Remember?
Yes.
صح ولا لا? We said that or not?
Yes.
صح? Makes sense? So the minority carriers, they are made from the broken bones of silicon. When they are broken, boom, They create electrons and holes. They are minority in this case because the dopant are majority. Those created from the dopant, they are the majority. Those who are minority in this case, they are those who created from the thermal generation. Okay? So thermal generation create what? The minorities in the N-type or the P-type. Do you understand?
Yes.
Things are getting spicy. That's why you need to build the picture. It's like a puzzle. You like puzzle? I love puzzles. Build the puzzle. That's very good training. خلاص? So the puzzle now becomes a little bit bigger. Good. So that current, the drift current, is heavily dependent on, therefore, on the temperature, because the people who are making this current are what? Are minority carriers, which are made from the thermal generation. صح ولا لا? So temperature break the bonds, create minority carriers. Minority carriers are actually those who are making this drift current, IS. Do you understand? That's why IS, or the drift current here, is dependent on temperature. So this after this. That's clear? Very good. So the drift current here is heavily dependent on the temperature. That's what we know. What else? Now, that drift current is created by the electric, is not created by the electric field, is actually moved by the electric field.
Yes.
Okay? Now, it does not, the barrier has nothing to do with that current. It just, if there's an electric field, they will exist. If it increase or decrease, it doesn't matter for them. What matters for them is that there are minority carriers. That's it. So if V naught of the voltage barrier, of barrier voltage, increase or is high or low, IS, the drift current, is totally independent of it. Okay? It is independent of that voltage. It's dependent only on the temperature because of the minority carriers that makes this current. That's it. So this is a fact. So this is fact number 1. This is fact number 2. Fact number 3. Oh, that's it. Fact number 3 is not something new basically. Here it's just telling us about drift current. That is the movement of the magnetic carrier. So there's 2 things only we need to remember here. Is that this drift current is dependent only on temperature and not on the barrier voltage. Good. Again, this picture, we didn't have enough. Okay, and then what happens? With the magnitude of current? Yeah, okay. That's what we said just now, that the magnitude of the drift current is unaffected by the level of the diffusion and or V naught. So, the drift current here is independent of the diffusion current. It depends only on how many minority carriers are here and there. That's it. The voltage here, the built-in voltage here, or the barrier voltage here, between this side and this side, that's the height of this, means V naught, this height, does not influence this current at all, the drift current, that is from the depletion region and to this side or that side, okay? And it does not depend on the current, on the diffusion current that is coming from the P-type to the N-type or the N-type to the P-type, okay? It is only dependent on the temperature. This is very, very important fact, okay? Very open fact. Okay. Now, the question is the depletion region symmetrical? What do we mean by symmetrical? Let's go back. Okay. Okay, the junction, where is the junction? The junction is exactly where? Here. So, this is whole depletion region. This is the whole depletion region. So, this area, or this distance on the N-type, this is N-type, صح ولا لا? N-type. This is one part of the depletion region. This distance, we call it Xn. Okay? And this region, let's use green. And this region, we call it XP. Just a dimension. So the question is it symmetrical? It means, is XP equal to Xn?
Yes.
Why?
Because
إيه صح, so what? صحيح. When the electron here meet the hole, boom, boom, bye bye. صح. بس still, is that xn equal to xp? مش شرط. It's not a condition.
Yes.
Let's think about it. We said that when the electron is moving from the n-type, diffusing to the p-type, it meets a hole coming from the p-type to the n-type, and in between they meet each other, and then boom, they are combined, they disappear, and that's end of story. So this electron leaves behind him or her, if you want, what you call a donor that is positively charged, and this hole leave behind it an acceptor that is negatively charged. So what we know that positive charge against negative charge. That's what we know. But the distance we don't know, meaning that the total number here of the positive charge should be equal to the total number of the negative charge. This is what we know. This we are sure. Because one hole meet one electron, bye-bye. Very good. To answer this question, we have to think about it. So, basically, we can answer this in the next slides, but I want to show you something here. So, all what we know here, then let's write, is that this positive charge, let's call it Q plus. And this negative charge, we call it Q minus. This I know. This is what we know. Make sense? Good? Very good. So, now, to know, these charges are what? Are the bound charge. Are acceptors and donors here in this area.
Yes.
Very good. Now, to know the number of charge here, because this is number of charge, this is number of charge. To know that, we have to multiply the density here of, and what? And A or and the... Yes? Go ahead.
B. And B.
B, there's no B. There's
D.
A or D. D.
يعني
here in this case, we have what?
we have
Donors.
Donors.
يعني and D. See, بدأت تتخلبط الأمور ها. يلا خير إن شاء الله. So we have to multiply here on this side the density of the donors by the volume. The volume, يعني this distance, multiply the cross section, yes or no? Yes or no? Because there is a cross section, yes or no?
Yes.
So we have to multiply by the volume A times X what? Xn. Good? Very good. On this side, however, we have the same story, but here instead of donors we have what? We have acceptors. يعني NA times exactly the same thing, A, the cross section, times the distance here. لأن volume حجم صح ولا لا؟ XP. Make sense? Now we can cancel A with A, yes or no?
Yes.
And the equation becomes what? NA XP is equal to ND XN. Now, the question, is NA is equal to ND? Not necessarily. مش شرط. صح ولا لا?
Yes.
Could be, could be not. Now, if they are equal, then XP will be equal to XN. وضحت ولا ما زال؟
Yes.
Clear? Now, if NA is much bigger than ND, then XP must be smaller than XN. صح ولا لا? Make sense or no? So if this is high, then this one, then definitely this guy must be smaller than this one. Smaller than this one. And if this guy go higher than this guy, and here I'm comparing this to this, I'm comparing this to that. Or in other words, we can find this equation, which is, this is exactly what we said, or is actually, it's exactly this equation. So this is what we said. Of course, there's QQ to make charge, because we were talking about number, but Q will cancel with Q. and A with A, and we get the same equation that we talked about. Now we can arrange this equation to make n, the big N on one side and the small x on the other side. So if NA is bigger than ND, then automatically Xn is bigger than XP. صح ولا لا? Make sense? Now look at this. It's from this equation. Make sense?
Yes.
So when it will be symmetrical? When? What's the condition? Exactly, when the donors and acceptors density is the same. خلاص? Now, if it is not the same, which one is the bigger? XP or XN? Depends. So, but how? It will depend. Look, very good, very easy way. So, XN is which side? Is in the N type. صح ولا لا? And NA is which side? In the P side. So, very good. If the P side is higher density than the, in terms of doping, highly doped than the N side, then the, okay, let's see, it's very a little bit tricky.
Opposite.
So NA is opposite, exactly. So that means the depletion region will be bigger in the lightly doped. So NA is which side? Let's say NA, which is this side. NA is in the acceptor, acceptor is in the P type actually. Yeah, and ND is in the N type, exactly. Okay, so let's say NA is bigger than ND, and A is bigger than D. That means if the P side is highly doped than the N type, then in this case, what's this? The depletion region in the N side is gonna be bigger than the depletion region in the P side. بس P type is highly doped. معناه the depletion region will be bigger in the area of less doping. صح ولا لا?
Yes.
You understand? This is the rule. Okay. So that means because XN is in the N type, which is this one, which is low doping, is actually bigger than the depletion region in the P type, which is highly doping. Do you understand?
Yes.
Very important rule and very easy to remember. Do you understand?
Sir, can you repeat?
Repeat. No problem. So you know this equation.
Yes.
Let's say an A, which is in the P type, is bigger than ND, which is in the N type. If this one, so P type يعني is more doped than the N type.
Yes.
So in this case, then the depletion region in the N type is bigger than the depletion region in the P type. صح ولا لا? This is number one. صح. The depletion region in the N type is what? Is lightly doped. صح ولا لا? يعني lightly doped will have the biggest depletion region part. Depletion region has in the N type and the P type, but where it will be bigger? It will be bigger in the lightly doped, in the low doping region. فهمنا ولا لا? Clear?
So doping and depletion region are inverse.
Yeah, exactly. So it's like inverse relationship between the higher doping, the smaller the depletion region. Okay? And the lower the doping, the higher the depletion region. Something like that. Okay? Things are getting spicy, but that's fine. It's no big deal. Alright, good. So, almost there. So, some equations. Of course, this will be provided in class XP, and distance, the depletion region for N, plus that one in the P. You understand? Clear? Good. So that plus that is this equation. You don't have to remember. All what you need to know is how it's dependent on. So epsilon S or epsilon Si actually is the permittivity of the silicon. Okay, divided by Q times this, but times V naught. So that means if the built-in voltage is high, the depletion region will be high. Do you understand?
So Dr. Barriers also depends on the depletion region.
The barrier voltage depends on the doping as well. Depletion region depends on the barrier voltage, and not the other way around. Do you understand?
Yes.
Okay. So the barrier voltage, if it is high, because we can make it high independent of the doping. We will see that next week, inshallah. And there is some students are using still the mobile and they think I don't see them. Please, do not use the mobile during class, please, okay? Alright, good. So, if now we can make V naught higher, somehow, artificially, then we can make the depletion region higher. If we make it smaller, the depletion region will go even smaller. Do you understand?
Yes.
Okay. We can see that next week. Now, this is the equation for the depletion region in the N-type, and this is the depletion region in the P-type, of course, using here in this case the depletion region width, okay, which is this one. Excellent. Okay. Again, all what we need to know is just how the equation moves or how it's working. Now, the junction charge, which is the positive or negative charge, which is the same, yes or no? Q plus is the same as Q minus absolute value. They will be exactly the same, but one is positive, one is negative. خلاص? Is equal to this equation, okay, which is very simple if you think about it. The cross section times the width will give me the volume of the depletion region. صح ولا لا؟ لأنه cross section مضروب في الطول تاعها، okay? Yes, that will be the volume of the depletion region. So this times this, boom, is the volume, times this. This is nothing but the density. صح ولا لا? So density times density, density squared divided by the density. It will be density. صح ولا لا?
Yes.
Make sense? Good. So this is nothing but the density. Density times volume is, boom, the number of charge times the charge will give me the amount of charge. خلاص? Just to make sure that the units make sense. That's why in the exam, if you make a mistake in the unit, you will lose half of the mark of that answer. Is that clear? Give you an example. 5 eggs and 5 watermelon. 5 حبات بطيخ و5 حبات بيض. 5 حبات بيض. You can take them. 5 eggs. You can take them by hand. Yes or no?
Yes.
So 5 watermelon. Can you take that while done? Even with with whatever you cannot. صح ولا لا? You will be crushed. صح ولا لا? Make sense? That's why the unit is very important. The unit is part of the number. People, they think that the unit is not important. No, it's important. In this course and in any engineering course. Okay? Do not make a mistake. Any wrong unit will be counted as half of the mark gone. Okay? Make sure that you don't do that kind of mistake. And that's why I mentioned this to you here. To show you how we can, with units, make sure that the equation is correct. And that's the role of units in engineering. It's not to waste our time. To understand the value, how big or small, and to make sure that the equation is correct. It's called equation checking. Very good. Now if we replace the depletion region with its equation, we can get this equation very, very easily. That's it. This is a summary of what we said, what we learned, okay? What is the PN junction? What's the majority carriers? We are not going to go there. What are the bound charge? What is the diffusion current? When you are home, you can read this. What's the depletion region, etc., etc., the built-in voltage, etc., etc. What are the minority carriers? You see, they are thermally generated. We have spoken about that now so far twice. Okay, last week and this week. Yeah, but today I checked. It seems that you forgot that. Don't forget that, huh? Now the drift current. What is the drift current? We talked about that. Okay, at the equilibrium, the diffusion current will be equal to the drift current. Diffusion current comes from the majority, the drift current from the minority. At equilibrium, boom, 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 they are the same. So what comes in goes out. Boom. So things are stable. Who has the book?
Everyone.
Very good. Open please page 57. Let's solve a problem. Let's solve a problem together, inshallah. And inshallah, it's an application of what we have learned today. Let's solve it now. And I need hands today, okay? I need somebody to help me to solve this problem because I need help. Okay? Good? So what this problem says, please open the textbook and read this. Consider a PN junction in equilibrium. That means everything is now stable at room temperature. And when we say room temperature, I don't have to tell you what's the temperature. It's 300 K. Now? Very good, excellent. Now the anode, what's the anode? P-type or N-type?
P-type.
P-type, very good. So the P-type was doped with Na is equal to 10 power of 18 per centimeter cubic, and the cathode is doped with 10 power 16. So Na is bigger than Nd or smaller? What do you think?
Bigger.
Bigger, why?
Because the power of 18.
How much in between? So is it twice? What's the ratio between them?
Doubled.
Double?
Yes.
Are you sure?
No.
What do you think?
100 times.
So what's the ratio between the two? How big? Is it twice and 3 times? Oh, you need a calculator?
100
You don't need that.
times.
Trust me.
10 to the
100
power 2.
times.
Huh?
100 times.
Exactly. 100 times. Very simple. So how do we know that? Basically this has 16 zeros and this one has 18 zeros. Between 16 and 18, how many zeros?
2.
And the other one will be what?
Cancel.
100. That's the 100 between. This divided by that is 100. Makes sense? She got it. Okay? So the acceptors are 100 times than the donors in this case. Okay? So it's not double or 3 times. Don't make mistakes. Okay? This divided by that is 100. Khalas? Understand? Excellent. Very good, very good, very good. So we have that, and the cross section is given with the unit. Now, this is what we need to calculate. What's this?
Number of
Yeah, go ahead. Yeah, continue. No one helps. Yeah, go ahead. This PP. What is PP here?
Number of
holes.
holes.
Let her speak. Go ahead.
Number of holes.
Please.
Number of holes.
It's not number, it's density. Remember this, huh? I want her to make mistake for everybody to remember what we are doing. We are talking about density. Do you understand? Very good mistake, and I want that mistake. This is the density of holes in the P-type. It's not number. Don't make this mistake. Because if you do this mistake in the unit, there is no unit for number. Do you understand? Number. But unit here in density is 1 over centimeter cubic or centimeter power minus 3. Do you understand that? That's the thing, okay? Very, very important. Do you understand why? Very good. So this is density of holes in the P-type, and this one is the density of what? Electrons in where? In P-type. A majority or a minority? Minority. When these two letters are not similar, that's automatically minority. Understand? When they are similar, boom, they are majority. To help you make it easy to understand. Because you were lost today. We talked about too many things, so what can we catch? I'm lost, okay? Very good. But you will catch when you revise, okay? And then this is the density of electrons in the N-type, holes in the N-type, bye-bye. We add here 0 just to say it's equilibrium. That's why we add 0 there. That's it. Don't worry about that. Boom, boom, boom. And this is what?
Barriers.
The voltage barrier, or the barrier voltage. This is? Depletion.
Depression region.
No, depletion region width. North can. Okay? The width. That's why we have W. We call it the width. What? Depletion region. You understand? XN, the depletion region in the N-type, is depletion region in P-type. That's it. And then the depletion charge. Very good. How much we have? 5 minutes. Let's solve this in 5 minutes. Hi. Who can help me? I need the first one. The first one. This. That's the holes in the P-type. Who has the answer? Wait. Here is your hand. Try. Make mistake. It's good for you. Trust me.
It's the same.
It's Na. Why?
Because it's the density of hole in P-types the same.
No, in holes in P-type, yes, because they are majority created by doping. We know that. Boom. So is that the acceptors? Very good. Khalas. So P, and how much is that? And A is equal to? 10, 18. What? See? See what I did?
Yeah.
If you miss this, you have half mark. If you miss this unit, you are missing everything. You are missing half of 50% of your money. Okay? Understand? Very good. Now, for now, we stay in the p-type. Huh? Now, give me the density of electrons in the p-type, NP, 0, just to say that we are in equilibrium. That's not big deal. How much is that?
Ni
NI
square
minus
over
NA. لا لا.
No. That's a mistake, but that's okay. صح. مين يعرف? You have an answer? We studied that. صح ولا لا?
yes.
Who revised? Now we can see that there's revision or not. صح ولا لا? Fair enough, huh? It's like mini quiz. You are waiting until the quiz. I told you don't wait until the quiz. صح. How to find the minority here of electrons in the p-type? So is equal to what?
Ni square over B type.
Over what?
Over
Na. Exactly. That's the one. Ni squared over Na, because we are in the p-type and Na is there. صح ولا لا? And Ni, what's Ni? It's given. It's given. صح ولا لا? Finish? Finish. Now we go to the n-type. Now the density of the electrons in the n-type is equal to what? And what?
ND.
And D, the donor's density, ND. We have it or not?
Yes.
We don't have to write it. And D 1016. خلاص? Per centimeter cubic, huh? Don't make mistakes. صح. Will holds Pn0 is equal to what?
NI square over
Ni squared divided by ND. Very good. Excellent. That's it. No, it's not that's it. Wow, V naught. V naught. So V naught, where is it? V naught, I will provide it to you, don't worry. It's actually very easy to remember. صح ولا لا? It's very easy. My God, what's going on? Sometimes this board is crazy, but that's okay. That's fine.
VT len.
Ooh, no, that's next week. Just a second. So, is equal to. So let's get that right in there. Okay. So V naught is actually VT, which we can calculate. At room temperature, how much is it? VT at room temperature?
300 Kelvin.
No, that's temperature.
25.6
That's T. 25? Unit what?
Volt.
millivolt.
That's the one. See? So it's 25 millivolt. You can't say also 26 is fine. See, refreshing, yeah?
25.
See, things are coming, you see. We are using what we know. Times the logarithm of
NA.
NA ND
Over
over Ni square. Use your calculator now. Okay? Never mind. You can do it at home. خلاص خلصنا V naught. W, we can get the W. The W is a little bit hard to remember, so let me try going back. Okay, let's see.
Square root.
Square root, a big one actually. Square root of 2 epsilon Si. We have it there.
Over Q.
Over Q, 1 over that, plus this. But we have calculated this, so just we need to put that value and we are good. And then later on, after that, we have to calculate differentiation in the n-type. We just use W that we calculated just now, put it in this equation, boom, 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 and that's it. صح ولا لا? We can make it even easier. ND is very small too compared to NA. صح ولا لا? It's like by 100. صح ولا لا? So this is like 100. صح ولا لا? Over, I'm talking about this, about only this. 100 over 100 plus 1. صح ولا لا? Like this. Make sense?
يعني كأنها
Then we cancel. صح ولا لا?
كأنها 1
فكأن هذه what?
1 very small.
يعني XN is almost equal to W. Depletion region كلها على ال N type. Very small, just 1% موجودة على ال P type. صح ولا لا? Make sense or no? So this one, if you do the same thing, is like 1 over 100 plus 1. صح ولا لا? Which is 1 over 100. صح ولا لا? It's like 1% of that W is XP. Clear ولا لا? Do we need a calculator? Not too much. Sometimes we don't need it. So you can see that it's very easy to make calculations in here. So most of the depletion region is where is in the N-type, where we have the donors, which are actually less dense compared to the acceptors by 100 times. It's big. صح ولا لا? Excellent. That's it. So and then the Q. خلاص. Q is very easy as well. Or what we need to do, come here. Very good. We can even play the same game. Very good. We'll talk about this ratio alone. Now we'll use, let's say, the red. So this one is like 100 times 1 divided. I'm getting crazy here. Right? Please write. This is times, not plus. So times 1 over what? 100 plus 1. صح ولا لا? So this is about almost 100, and this is about 101, almost 100. So this is also almost is equal to what? Is equal to 1. صح ولا لا? 1 of what? 1 of, what's the unit here? Is actually the smallest one, which is an A. صح ولا لا? Then an A, we took it as a common factor here. You understand? So, like for example, here we said an A is 100 times ND. So we can replace this by 100 times ND. And then we bring ND, this one, outside. صح ولا لا? And the same thing for ND here. Okay? So ND with ND bye-bye, but we have ND here. So boom, boom, boom. And we have to multiply by ND, right? ND, by the smallest one, yes? In any case, just play with the numbers, you will see what I'm saying. That's fine. That's it. So we can then, in this case, get automatically the junction charge. And what else? That's it. That's it. Finish in 5 minutes. So see you inshallah next week. We will try to put this device in a circuit. Any question? Any question? All right. Thank you very much. And